Happy Thursday, everyone. So just real quick, as we're starting this video, there's construction going on in my parents' house. So if you hear a lot of bangs and just tool noises, that's what's happening. So today we are focusing on indefinite integrals. So we're starting on 5.3. And so looking at our triangle of what we are focusing on, and I know we haven't looked at this for several days, but we have been focusing on area from slices. And by area, it could be volume, it could be other things. It's just adding up very small pieces in order to get a whole. And then eventually we're going to be over here where we have a rate of change giving us a total change, and that is the fundamental theorem of calculus. But today we're focusing on the top of our triangle. We're focusing on antiderivatives, also known as indefinite integrals. So before we even begin, I did give you some antiderivatives last time, but the thing is, an indefinite integral doesn't have one answer. An indefinite integral has an infinite number of answers that are all in the same type. And we will get to see that later on today. The formal definition of an antiderivative is a function, capital F, is an antiderivative of little f on an open interval. And I'm going to put this in parentheses, first off, just to remind you that an open interval is with those open parentheses, but also just that this is needed for the definition, but it is not very revealing about what it means. Open interval, and that interval is from A to B, if the derivative of capital F is equal to little f of x for all x in that interval. Oh, did I misspell that? I did misspell that. Let me erase it on that interval. Okay, so that's really like formal, but what that means is, let's say that f, so little f of x is equal to 2x squared plus 7. Then this is the derivative of some other function. And that other function for this could be f of x is equal to, so we're going to go up in power like we did last time, 2/3, and then plus 7x, and then let's just say plus 3. So the derivative of capital F of x is this guy. But we also have maybe capital F of x is 2/3 x cubed plus 7x minus 27. That constant can be anything. And so if you are looking for the antiderivative of little f of x, so you're looking for the antiderivative, then you cannot find the antiderivative. What you can find is the class of antiderivatives. And so in reality, what we would want is the class of antiderivatives is 2/3 x cubed plus 7x plus c, where c is any constant or every constant. So any constant, bloop, any constant. And in fact, this class is called the general. That'd be funny if it was just called the general, but it's the general antiderivative. So whenever you hear the general antiderivative, it's not one, it is derivative. It is an infinite number of antiderivatives. It is all of the The way we write antiderivatives, so instead of putting limits of integration here, we leave those blank. So this symbol just means, in the case when you don't have limits of integration, is find the general antiderivative or the class of antiderivatives of the function following. And so let's say that we have 17x to the fourth minus x to the negative 3 plus 2 dx. So we always want this dx there. If you drop the dx, usually that means some points off on your quiz or homework. So remember to write your dx at the end of this. But anyway, this would be, okay, so we want to go up in power. So we're going to have x to the fifth. And then we're going to divide 17 by 5. So we're just reversing that the derivative process. And so if you were to take the derivative, you pull down that 5, and when you multiply it with 17 fifths, it cancels and you have 17 again, and then you subtract from 5 and you get 4. Then we're going to have minus, and we're going to go up in power. So negative 3 plus 1 is negative 2. And then out front, you have 1 over negative 2. So that's going to simplify. Plus 2x plus c. Always, always, always remember the plus c if there are no limits of integration. And always remember the dx when you write an integral sign, whether it is definite, indefinite, or for the fundamental theorem of calculus, which we will get to later. But yeah. This is the class of antiderivatives, or the general antiderivative of 17x to the fourth minus x to the negative 3 plus 2. All right, so here's a cheat sheet of some antiderivatives you might need. And so if you are taking the antiderivative of x to the n dx, where n is not equal to negative 1, then this is going to be equal to, remember, if you had a constant out front, you'd divide that constant by n plus 1, and you would go up by n plus 1 plus c. Plus c. As long as this is an indefinite integral, include that plus c. Some others you might know is the antiderivative, or the general antiderivative of sine of x dx, is negative cosine of x plus c. Because remember, the derivative of cosine is negative sine. So the antiderivative of sine will be negative cosine. And then similarly, the antiderivative of cosine of x dx is sine of x plus c. And then the last one I want to put, actually I don't know if this is the last one, but one of the last ones, if you have 1 over x dx, which is the same thing as x to the negative 1, so we're kind of going back and taking care of this case, it is natural log of x, and usually it's the absolute value of x, plus c. And then just in general, here are the rest of the reversing the trig derivatives. So remember, the derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. The derivative of cotangent of x is negative cosecant squared, so the antiderivative of cosecant squared of x is negative cotangent x, and etc., and etc. If you need to look up these trig, we will go into general. If you notice, we have not told you what the antiderivative of tangent is, or cotangent, or secant, or cosecant. We are going to end up learning those when we do U substitution of the antiderivatives, I think in next week, possibly. But yeah, you might want to write these down somewhere convenient. Also, we'll go more in general into these later, but you might need them for your WebAssign. If you have cosine of some number times x, so that's on the inside, dx, then your antiderivative is going to be 1 over that constant, 1 over k sine of kx plus c. So this is reversing the chain rule. So if you remember, if you look at this, then if you were to use the chain rule on sine of kx, and again, if you put a 5 in here, it'll be a little bit easier to see, then the derivative of sine of 5x will be 5, well, it'll be cosine of 5x times 5. And so this 1 over 5 would be to cancel that 5 that comes from the chain rule. So this is just reversing the chain rule specifically with cosine, and then you can do the same thing with sine. So the antiderivative of sine of kx, where k is a constant, is 1 over k cosine of kx. And then we need to remember there's a negative here because the derivative of cosine is negative sine. So the antiderivative of sine is negative cosine plus c. So again, these are just if you need them for your WebAssign. We'll go way more in depth into this type of antiderivative again next week. All right, and then the last two antiderivative formulas I want you to have is, if you look at the top of the screen, the antiderivative, or the indefinite integral of e to the x dx is e to the x plus c. And then just continuing the pattern of what's going on down here, if you have the antiderivative of e to the kx dx, then this is going to be 1 over k e to the kx plus c. Again, this is just reversing the chain rule. So I would really recommend at this moment, take a screenshot of this panel, and then make sure you have this ready to go in your notes for doing homework and etc. All right, so let's do a few of these just as examples, and then you will get a chance to do some as well. So as examples, we have, let's do the integral of 14x to the 3 halves plus, and then let's do sine of 11x dx. All right, so first thing, all those properties we learned from the last thing about integrals, about how you can split them up over plus signs and you can pull out constants, they are all still true. And so if you want, you can rewrite this as 14 integral of x to the 3 halves dx plus the integral of sine of 11x dx. So you can split it over plus and minus signs and pull out constants. And so whenever you take the antiderivative, you're going to end up with, you're going to add 1 to that 3 halves, which makes it 5 halves. So x to the 5 halves. And then 1 over 5 halves is 2/5. So 14 times 2/5, x to the 5 halves. And then since this is all, I could add a plus c here, but I'm just going to do plus c at the very end of all this process. So plus, which actually will turn into a minus because the antiderivative of sine of 11x is negative 1 over 11 cosine of 11x dx. Oh, nope, sorry. I should not have written that dx. I was just not thinking. But instead, plus c. Don't forget the plus c. But this simplifies down to, what would that be? 28/5 x to the 5 halves minus 1 over 11 cosine of 11x plus c. Okay, so that is how you would take an antiderivative of something with a power and sine or cosine of a number x. So let's do another one. Let's do the antiderivatives of, let's say, negative 7 over x plus e to the negative x minus the square root of x all dx. Okay, so we want to split this up and rewrite it. So if we look at this guy, then you have that this is equal to negative 7 times the integral of 1 over x dx plus the integral of e to the negative x dx minus the integral of x to the 1/2 dx. Again, in almost every case, you're going to want to rewrite a root or as something over an x into a power form for antiderivatives. The only one I don't rewrite is something where the x is just on the lone on itself on the bottom. So when we take these antiderivatives, then we're going to have negative 7. And then remember, the antiderivative of 1 over x is natural log of x. And again, I'm going to add the plus e at the very, very end of this. Plus, and then you have e to the negative x. So I want to just kind of point out this negative x is the same thing as negative 1 times x. So the antiderivative is not just e to the negative x. It is going to be 1 over that constant negative 1 e. Oh, I meant to do that in black. Okay, so that's 1 over negative 1 e to the negative x is the antiderivative of that guy. And then minus, and so you have x to the 1/2. So x to the 1/2 plus 1 is x to the 3/2. And then times 1 over 3/2, which is the same thing as 2/3 plus c. And so this cleans up to being negative 7 natural log of the absolute value of x minus e to the negative x minus 2/3 x to the 3/2 plus c as the antiderivative. So what I'm going to do is on the next slide, I'm going to give you some examples to do on your own, and I'm going to play some music on this video because I want you to do it while you are watching this video as if we are in class. So I'm going to give you like 4 of them, and I'm going to give you about 5 minutes to work on it. And if you need to press pause before I give you the answer to finish these, then do so. Okay, so you are going to work on these problems for the next 5 minutes. Before you start, I just want to point out some things, especially number 2 and number 4. You want to think about, especially this piece, how you might rewrite this so that you can use the rules that you've been given to find these antiderivatives. So I'm going to start some music, and you just work on these. Okay. If you're still working on the problems, I am going to reveal the answers. And so press pause if you're still working on them in 3, 2, 1. So here are the answers you should have gotten on these 4 problems. If you did not, I might recommend maybe contacting me during Zoom today from 3:30 to 4 and seeing what went wrong. Yeah. And so to finish up today, I'm going to give you a you-do problem, which is just going to be some more of these, maybe a little bit more challenging, and then also go over yesterday's you-do problem. Okay, so I want you to do 2 integrals. So the first one is x cubed plus 3x minus 4 all over x squared dx. So this one is going to need to use a little bit of creativity before you can even start taking the antiderivative. The next problem for you do is the general antiderivative, or the integral, of 8x minus 4e to the 5 minus 2x all in the power dx. So I want you to take these 2 integrals as your you-do problems. So now let's look at yesterday's you-do. Okay, so this was yesterday's you-do problem. So you were given the derivative of f of x, not the derivative. The definite integral from 1 to 6 of f of x dx is 7. The definite integral from 4 to 6 of g of x dx is 2. One moment. Okay. And then the definite integral from 4 to 6 of f of x minus g of x dx is equal to 9. And you were asked to find what is the definite integral from 1 to 4 of 12f of x plus 3 dx. And so we're going to go down a little bit and zoom in. And so you needed to use those rules from previous, from that lecture last time to solve this. So first, I think it would be good to solve for, let's see here, let's find f of x from 4 to 6. So we know from 4 to 6, f of x minus g of x dx is equal to 9. Then we can split this, and we can have 4 to 6 of f of x dx minus, from 4 to 6, g of x dx is equal to 9. But we know that the antiderivative from 4 to 6 of g of x is 2. And so if we go back here, this is equal to 2, which means what minus 2 equals 9, which gives us this guy is equal to 11. All right, that is a very ugly 11. I'm going to fix that real quick. Is equal to 11. The equal sign looks a lot like the 11. But anyway, so we've got that's equal to 11, which means we can now find what 1 to 4 is, because we know the integral from 1 to 6 of f of x dx is equal to 7, right? But we can split this at 4. So we've got the integral from 1 to 4, f of x dx, plus the integral from 4 to 6, f of x dx, is equal to the integral from 1 to 6, f of x dx. So this is that we can split an integral at a midpoint, and we know from 1 to 6 is 7. We know from 4 to 6, it's 11. So what plus 11 gives you 7? And the answer to that would be -4. So we know from the antiderivative, the definite antiderivative, not that, I'm sorry, the definite integral from 1 to 4 of f of x dx is -4. And so the last thing we need to do is just put this together into our original. So we've got the antiderivative, not the antiderivative, the definite integral from 1 to 4 of 12 f of x plus 3 dx. And we can split this up so we can pull out that 12 from 1 to 4 f of x dx plus the integral of 3 dx. And so when we solve this, well, we know that this, from our previous work, is negative 4. And so this will be 12 times negative 4. And then, oops, this should be a 1 to 4 there. Plus the antiderivative of the definite integral of a constant, which is 3 times the difference of your limits of integration. So you have, this is equal to negative 48 plus 9. So your overall answer should get negative 39. Negative 39. So this is what yesterday's you-do should be. Yeah, so this is the work from this. I think there's several of these in your 5.2 WebAssign. So just a few announcements before we move on. First, as always, there's a Zoom meeting today at 3:30 to 4 p.m. So if you have questions about Monday's quiz or today's you-do or yesterday's you-do or just anything in general, I will be posting the link to that on announcements as well as the password. So you will need a password to access the Zoom meeting, and that is just, it's going to be posted on the announcements on Canvas. The other thing is later today, I will be posting a paper homework. So keep your eyes open for that. It's going to be over Riemann sum stuff and maybe a little bit of these antiderivatives. I just want to give you feedback on how to write some of these problems. So be looking for that. It'll be posted later tonight. I am working on grading your quizzes. You can see my progress on Canvas, some of you. I'm grading one section before the other, and I'm doing it problem by problem. So hopefully I'll get that back to you. I thought it would only take a couple of days, but I think it'll take me a little bit longer. Monday at the latest. But anyway, I hope all of you are healthy, physically, mentally, emotionally, and that you are keeping up with your schoolwork. All right. Have a good day.